Our model of a rectangle of wire within a magnetic field needs to be further studied. The electromotive force, and therefore the current generated in our rectangle, are proportional to flux linkage. N phi is flux linkage, and it is the flux linkage divided by time that Faraday's law tells us is equal to electromotive force. Flux linkage is equal to the magnetic flux density times the area of the loop times by the number of loops times by cos theta, where theta is the angle from the perpendicular to the plane of the field and the plane of the loop. To work out the electromotive force, all we have to do is divide this by the time it takes to spin. We are dealing with circular motion here, so a simple time isn't important. Instead, we want to know how quickly this loop spins on its axis, and how much of this circle the loop finishes up at. The speed the loop spins around is the angular velocity, which we dealt with in circular motion concepts. It is given the symbol omega. This is the angle divided by the time. So if we want to know the amount of a circle the loop has spun, we need to times it by the time. Summing all this up, the flux linkage per unit time, the magnetic flux density, the area of the loop, and the number of loops, the amount of the rectangle showing to the magnetic field, and the speed of the loop spins around are all summed up to give an equation for electromotive force for any spinning rectangle in a magnetic field spinning on its axis. The electromotive force on such a loop is equal to the magnetic flux density, B, times the area of the loop, A, times the number of loops, N, times by the angular velocity, omega, times by the sine of angular velocity, omega, times the time the loop is spinning for, T. Complicated, I know, but complete. Electromotive force on a loop is equal to BAN omega sine omega t.